Hey everybody, this is Larry. This is day 30 of the July Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, the last problem of the day. Yay! We're gonna have an intro one of these days from my weekend trip. It's just been so exhausting in a good fun way. I climbed a mountain, almost died, lost my helmet, lost my camera almost, and I found it again, lost and found, cracked my phone. What else happened? Just like general altitude sickness. Yeah, it was very fun. And follow me on Instagram and hit the like button on my photos if you're into that. I posted a couple of photos, and I don't know. Maybe you don't have to follow, but just like them anyway. It makes me feel good rather. But yeah, all right. Let's take a look at today's problem. Bitwise or of subarrays. Okay, so given an integer away, we've been doing a lot of bitwise problems lately. My apologies this week though, because I've been just traveling, generally out of sorts. Bitwise problems are kind of very interesting in that they're very particular and not that useful, really. I mean, you could say that about a lot of things, or some people do. But it's not even that it's not all that useful, it's very particular. So a lot of this is, you watch me solve it or whatever. It's not, these are kind of like my odd observations that you would make from, just like from the past, right? What I mean that is that if I go by fast, it's not because, well, I was gonna say it's not because I haven't seen it or I have seen it before, which is actually, have I seen this one? There's no sub button. Wow, this is a new problem for me. But in any case, yeah, I mean, honestly, I am getting old, for better or for worse. Whether I've seen them before or not, I don't remember them, so that's one. But when you make an observation, that's part of learning and kind of being fast, is that you've seen it before in some form, right? Maybe not the same identical form, but something similar before. It's like if you, I don't know, do something, it is a dumb analogy, but if you do like, I don't know, the multiplication tables, right? 1 to 9 times 1 to 9, you memorize that, or you do it like, maybe not even memorizing is the wrong word, but if you do it like 20 times every day or whatever, I'm sure you get better at it too, right? May not be good, but and may not even be useful, but you just get a little bit better and you notice things, right? But yeah, so it's something like that, but also for bitwise operations. We talked about maybe I could have done it a little bit better, but bitwise and bitwise or and the properties of it. I didn't go into it in detail. Last night was a mess because I had a red eye. Today I'm a little bit better, though not fully recovered still, and as you can guess, it is very hot today as well. So we will see. Also, my training, I ran 5 miles easy, so just trying to get back into a little bit. Marathon training is silly. Why am I doing this? Why did I sign up for this? In any case, let's take a look. We have a problem that we haven't solved before, so this is a new video. We will see how I go. We have 898 bitwise OR of subarrays. Given an integer array OR, return the number of distinct bitwise OR of all the non-empty subarrays of OR. The bitwise OR of a subarray is the bitwise OR of each integer in the subarray. Say what? The bitwise OR of a subarray of one integer is that number. Okay. Okay. Return the number of distinct bitwise OR. Okay. That is interesting. I mean, the first thing I would say, I don't know this one. They're at most n squared distinct ones, right? Kind of, right? And the reason why I say that is because it's hard to have all n squared distinct bitwise or situation, because it is. I don't know if I know the term. I feel like I want, but bitwise OR is almost like an incrementing kind of function, right? I'm really bad at terms today, so maybe I don't remember exactly the mathematical thing for it. But what I mean by that is that you could keep on adding numbers and it will just keep on getting monotonically increasing, right? Meaning that like you just keep on adding numbers to the list. And then the question is, well, how many unique numbers can there be? I actually don't know if there's a cool way, but the way that I would try to think about it is that is this, right? That initially we start with n squared, but keep in mind that there are only 32 bits, right? Or yeah, 30 bits from to 10 to the 9, but roughly 30, 32, whatever, right? Doesn't matter. And what I mean by that is that, like I said, bitwise OR is incrementing, right? I'm too lazy to kind of write this out, but you can imagine a number that has 10 binary digits, right? So that it's a little bit easier. And this is going to be a vertical one. So maybe you have like one, let's just say maybe the number is, I don't know, 20. What's 20? 16 plus 4? Right, maybe that's too boring. Right. 16, 8, 4, 2, 1, right? So you have like 10,100 in binary. And then the thing is that if you kind of XOR it with any number, that, or sorry, not XOR, regular bitwise or any number, a number of things can happen, right? But it means that, okay, there are only two cases. Let's say you just do another random number X. So one case is that, well, it gives you the same number, right? And what I mean by that is that maybe it's all zeros, and it could be all zeros, it could just be a zero, right? Or there's a 1, or here, and it doesn't change the answer, right? Because X is, like, if all of these doesn't matter. The only way that it changes is if it's one of these bits is the answer, right? Or it's the X that we're adding to it. Because then now, when we bitwise these two doesn't change the previous one, but these two, now you flip the 0 into a 1, right? And so forth. And then the question is then, what happens? Well, what happens is that if you kind of look at it in a kind of sweeping kind of way, maybe sliding windows, maybe not kind of way, then what do you do? Well, that means that looking at here, and now let's say we have a 30-digit number. Maybe I should have gone down instead. This is so annoying to write. Like, right? Well, maybe this is 0 to 20, and then now we have 20 is 0 to... Maybe I should have done that as well. And then now you have X is 0 to, some number, and you're trying to like get a new number, right? And so the new number with the X with the O, I keep saying XOR, my fault. It's gonna be at least this, but then maybe we can change one of the bit to a 1. And we don't know which. I mean, it doesn't matter which one per se, but it could be one of them, right? Okay, so that's the first thing. And then the second thing is that, well, if you say it that way, that means that the only way this has two cases. One is that it stays the same. The other is that it changes, right? Okay, that's a very trivially true statement. But yeah, if it changes or the same, well, if it stays the same, then we could, well, then there's no new distinct bitwise OR, right? But if we want to get a new number, what does that mean? That means that we can only, the smallest amount of move that you can make is just change one digit. So let's just say we change one digit. It doesn't matter which one. But then now, essentially, you went from this number that has 2 bits, 2 binary bits, to 3 bits, right? And then now, let's say you do another one. Just change another 0 to a 1, right? Now we have 4 bits. And then ... And all the way, say, up to 30, right? And what that means is that for each number, let's just say this is the left side of a subarray, right? The start, the beginning of a subarray. You have one number, right? And then you just kind of, if this is the left side, that means that it can at most change 30 times, right? And if that means that now we went from n squared maximum case to d times n, right? Where d is, say, 30. Like d, I say d for digits, right? And then now the question, now you can think of it another way, right? Is that, okay, well, now we know that it changes if one of the bits is of 1, right? So then, now the question is, okay, there may be other ways to implement it. This is just the first one off my head. Is that now, given an array element, let's say we start at one element, we can just keep asking ourselves if we're able to do this fast. Let's say we start at this one. We may say, give me the next number that gives me an extra bit, right? And this may be a 2, right? And maybe if there was a, I don't know, 11 or that's 12, and maybe it's this afterwards, ... right? And you will only have to do this 30 times or d times, right? So that means that if we're able to move quickly to the next change, we can do this in O of d times n time, right? And that's not quite true. Let me rephrase it. But and what I mean, times the number of moves, right? Or the time of the move, and maybe that could be you go log n, maybe, guess, maybe not. But yeah, so that's basically the structure that I think I want to have. And you can maybe do this in I'm trying to think whether I can. I think there's a dynamic programming solution. I don't know if that's what I want to do. The dynamic programming solution is I mean, it's not quite dynamic programming. It's more like it's more like a depth first search, really, in that you don't revisit states. But the proof of that bound is harder. But let me YOLO this for a second, right? But this is just the idea. And then now maybe we can set something that's similar to dynamic programming. And it's not really dynamic programming. We just don't want to memorize everything. Or we just don't want to... we don't even have to return anything, right? So maybe we go... I name things Go just for now. And then index and then the current XOR, right? So then index is going to be, maybe I won't use cache for learning purposes. Index is just 0 to n, and then current is the current or bit mask, right? The proof is kind of tricky though, but let's just say we have something like scene is you go to set, and then now we just write a lazy thing of like if this is in scene, then we just return. Otherwise, scene.add index current, right? And we can also add that scene for this go function, but then maybe you have like an answer set, right? And keep in mind that in the worst case, this is going to be hold d times n elements, right? So answer.add, we want to add current to the set because now this is a possible distinct bit mask, right? And then now we just go for now we just kind of go to the next number, right? So index plus 1, current or array sub index, and that's it, right? And that's really it. There's no like, I was going to do some tick no tick, but that doesn't even make sense. The reason, I mean, you can do it that way if you want to. There's another thing, but the reason why you do this is because the end tick no tick is kind of like the end ending the current subarray and not ending it, right? But this is adding it. This is the path of ending it, right? Is that when we set current as when we add current to the answer set, that means that it is the end of the subarray, and when we want to continue, well, we just continue, right? And the reason why this is faster, right, is because of this possible states. And we'll go to proof in a little bit. It's a little bit trickier than the other thing that I was saying. But then now here we just have to start from 1 to n as the beginning of the subarray, and then just go I oi or sub I. And then we can return length of the answer afterwards. I think that's right, maybe not. I forgot to check for yeah. Right. Why is this 3? 1, 2, 2. Well, the easy thing is that we can print it out. I'm wondering which one's missing. 1 and 2, so it's missing 1 or 2. Huh? That's wonky. Let's see. Actually, I do not expect that. Index, yeah, just oh, I see. It's because we add, this goes to the end, so then now we go to here, but then this doesn't add this. I'm just a silly boy. Okay. right? Let's give it a YOLO submit. Yeah, it's a little bit on the slower side, but I mean, you saw the code; it was done very quickly. And you may ask yourself, isn't this n square? We start at every index, and at every index we just kind of, even if there's a tick, this is the tick, no tick, it still goes through the entire loop, right? And the key reason why this is not n square is because of this thing, the scene thing, right? And the scene thing, and this part will kind of bring it back up a little bit. We kind of went over the house, the mechanic, but it's still very tricky for me to kind of explain. So let me give it a try, but my apologies if it's not super whatever. But the idea here, and I'm drawing it out, that's why I take a little bit. The idea here that's different is that is the same as before, right? Let's say we have 20, which is this, right? And then now, let's say we're going from left to right, we're sweeping. Then now, so either we have a new bit or not, right? But after a while, that means that, as we said, when we kind of sweep, we only change one bit at a time, say, right? And because we change one bit at a time, starting at this point in the future, they're at most 30 values, right? Or something like that. But it also means that there are a lot of repetitions, right? Because this is kind of tricky to prove. I mean, I forget. There's even a name for this, but I forgot it because it's like, I don't know. For me, I feel like it's just a name, some crazy kid's name, and I don't know. But it's this idea that this is the smallest number coming from the other side, right? So what I mean by that is that coming from the other side, you grab any number of things, but if the number is coming from the left side monotonically smaller, then now that means that when you get to here with this state, you do not have to branch out anymore. It's kind of the principle of this as well. So then now, because as we said, so given some number x, right? On the right side, we only increase by 30. But on the left side, coming in here, let's say this x has, I mean, we say 30, so it's going to be 30 minus whatever. But let's just say for argument, let's say it has 5 bits, so maybe like 110, 1101, or something like that. That means that on the left side, in this case, there are at most 5 different values leading up to it, coming to here, right? So that means that coming into here, they're really at most, because you can think that okay, so there's an incoming value, right? And then that incoming value we OR it with this x, right? But after this x, after it comes out, so something comes in, it does the OR function of the x, and then something comes out, right? Well, the something comes outside, there are at most 30 distinct values, right? I think that's the way to kind of think about it. It means that no matter what the inputs are going in, well, that's not true. But because you know that this property on the left side coming in is also incremental, right? Meaning that let's just say if you want to take it like a prefix some kind of way, or just a prefix kind of way, you know, you have this gives you an input, this gives you an input, this gives you an input, and this gives you an input, ... right? And if you kind of like analyze it in reverse in the same way and for the inputs, then it just means that you know, this has an input. The smallest one element to the left thing has a thing that has let's just say k bits, and then next to it, if it wants to change by a little or it doesn't, then it's just k plus some other, maybe 1 bit, maybe 2 bit, but ... all the way. That means that they're only at most 30 distinct thing, right? Because every time you stretch to the left, at most it's either the same or you have 1 more bit in the worst case. And if it's the same, then, well, your input's just going to be the same. So that means that coming into this particular x, you have at most 30 possible inputs. And because you know this number, well, if there are 30 possible inputs coming out this way, there are at most 30 possible outputs coming out this way, right? And they're kind of deterministic, right? There's no like combinatorial craziness, right? In fact, it probably should be less in the sense that they merge bit, all right? So that means that yeah, so that's kind of the idea, is that now they're only for every x, because this is I call it incremental. I don't know if it's quite the right term, but an incremental thing to the left, and as a result, according to the x, there are most dirty outputs going in, out, and that means that there are only dirty unique outputs coming every step, right? And as a result, that means that this does what we said. This is O of D times N, right? Hopefully that kind of makes sense. I don't know. It's a little bit hand wavy for sure, but this idea is actually comes up quite a bit in harder problems. Maybe not quite a bit. I don't know, but a couple of times, say. So yeah. But that's it. So what's the complexity here? We already did it. It's kind of as we said, this is going to be O of, well, current bitwise or mask. There are at most dirty distinct inputs, right? And this is O of N, right? So that means that in total, and we do O of 1 operations here and there. So yeah, and because of this scene, we don't branch out if we already done it. So that means that this is going to be O of D times N, and that is your time complexity. Yeah. We're also going to do this loop, but it's still frozen, even though, because you can assume that this is O of 1 due to the caching, if you will, or branch bounding. But yeah, that is all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy to your mental health. I'll see y'all later and take care. Bye bye.